so that this is available later. Started recording. Hi, welcome. We're doing a general update on IPDK. This has been recorded, so if you don't want to be recorded, drop off now. Today we're going to go through some of the update of where we're going in the next several months for IPDK. Can be pretty quick. So let's see. Let me pull up the website first. So sharing the website. The first change that will happen, hopefully really soon, is that on the GitHub, both the website and OVS will institute the check-in policy from SPDK. So this will enable anyone in the community to make posts to any of these repos. And then the core maintainers vote on those patches to accept them. We've had a couple folks post issues, things that they found while they were trying it out. So that has been working, just the sort of basic GitHub, but now we'll have more of a CI/CD flow in place, and all of our patches from Intel will also be going through that same flow, so that it'll all be in open source development at that point. In that flow, we do want to get to the point like we have with SPDK, where when a patch comes in, change is made, that we go and automatically go run some regression tests on all the different targets that we have. And so just like SPDK will go and run on kickoff, vendor specific tasks to go and run and say, make sure that patch works for this, hardware vendor's devices. We'd like to reuse some of that mechanism so that for the different hardware vendors, they can have their hardware checked against any changes that have been made. So we also would like to put out some tests, even if they're just simple, smoke tests, to say, all right, well, I reran the networking recipe on this hardware and checks out. So we'll start to get that set up in the sort of imminently, and have that available for other folks that want to put their have their targets checked against the images. We have updates to the documentation. We have updates to the block storage recipe coming, as well as, just like we have a networking container, we have a storage container coming pretty soon. What I wanted to talk about today is when both that networking and that storage container are in place, what are the sort of main usages that we're going to go and sort of put both of those together and sort of make work as a system, both networking and storage simultaneously. So I'm going to switch gears here and just throw up a slide, which I'll make available after the call as well. So if you can see this. Now this release cadence is around what we're doing here at Intel. I think that there's other work going on that may certainly add to this. But what we're looking to do is focus on the the bare metal hosting use case first. So you take both the networking and storage recipes that are out there today. Where they have commonality is if you look at both of the recipes in the beginning, there's a section on, okay, well, here is how this function works for KVM, and this is how this function works for a bare metal IPU, DPU type of device. And where that's common is they both have, sort of a vhost type of functionality. In KVM, it's actual vhost, and in the IPU, DPU, it's it's potentially inside the hardware. And so in this first bare metal hosting usage, we will commonize that KVM functionality of adding and deleting devices into the instance, the compute instance. And what happens is when you're doing this with KVM, your compute instance is a VM. When you're doing it with an infrastructure device, your compute instance is an actual host. And so except for that difference, we want to have all of the control planes that are coming out of the target and out of IPDK at the infrastructure application interface, have them all be common. So if you sort of can get this use case to work with KVM with VMs, then you should be able to also reuse that functionality in IPDK to have this work for a bare metal host. And so what we mean by a bare metal host is that you could have you could set up a cloud management system where you're instantiating images into VMs using KVM, and sort of serving I/O into each of those VMs. You could also do the exact same function, but put that image on an entire host. And on that host case, there's no place to stand for the OVS or for the SPDK or for your infrastructure functionality. That's where you need the infrastructure device sitting in front of the host to be able to do all those things and still preserve the host as a single unit, where you're selling the whole chicken instead of the pieces. And so what this first release will do is we'll make that control plane common across the two cases. So it won't matter if you're running your infrastructure inside the host to serve guests in the VMs, or you're inside of an infrastructure device serving that bare metal host. So we make that common in that first release. And then what we're using for to actually implement that infrastructure is P4 OVS on the networking side, just like in the current networking recipe. And then for storage, for block storage or software-defined storage, we're going to do all the plumbing for SPDK and use I would say a sort of a ideal one-to-one target mapping inside SPDK, so that we show how the plumbing to get those block storage requests out of the compute instance into the infrastructure and over the network. But we're not going to be doing anything more advanced in terms of distributing that storage around in the infrastructure. For now, we leave that up to the user. Very similar to P4 OVS. P4 OVS is coming with a very simple P4 program that just is doing what's called simple L3. So you can think of those two control planes as sort of starting points where, all right, well, to really do bare metal hosting inside P4 OVS, I need to be able to do tunnels and ACLs and maybe even connection tracking, all of these things. In order to do, the functionality you need for VMs to do OpenStack or whatnot. So we leave that to the user, and we give you the mechanism to go recompile your P4 program to do what you want to do. And same thing for SPDK. We give you the plumbing to get the pieces in and out of the your storage backend, and you can use SPDK, or if you already have an application built on SPDK, just drop it right in. But we're purposefully keeping those two pieces simple to be able to just focus on this sort of compute instance facing functionality, where we're trying to make that all of these different sort of hardware, software implementation differences, all the different targets that we have, try to make that common. Questions about that? Cool, cool. All right, and then in the recipes, you'll see that there's sort of like a first part that talks about bare metal host, talks about KVM, and then the second part talks about VMs. So it's called, in the recipes, host virtualization. So it's exactly like doing the KVM target and the infrastructure device target at the same time. So you have a little bit of the hypervisor still running in the host for all doing the things that you need to do for adding and deleting images onto the host, making sure that those images are secure, doing all those, allocating memory and other things that are not part of the I/O. All of that stays on the host. And then the rest of it has been moved off of the host and into the infrastructure device. And so, that case doesn't necessarily have a software, hardware, complete equivalent. It's really a special case of where you're combining the two concepts together. And then splitting the functionality across the two, and then having a communication channel in between so that the two pieces can stay in sync. And there's certainly two ways to do that. You could have the thing running on the host be the be the primary, and the thing running on the infrastructure device to be secondary, or vice versa. So we call that out in the recipe. So this is sort of a second step on top of bare metal hosting. It's, you're starting with bare metal hosting, but now it's almost like, you're hosting your own OS and application on the host, and that application's job is actually to serve VMs on that host. So we will do that one second. And also the third recipe on the website around Kubernetes, that would happen around the same time. It has a lot of similar concepts where there is a communication channel between the logic that is in sort of instantiating or imaging the containers, and then there's another piece on the infrastructure device or inside the infrastructure, like if it's in KVM. Handling the data plane. So from a sort of 5,000 foot view, they're really similar. It's just depends on how you're chopping up the host. And at the same time, I put these interfaces up on the website yesterday, but around this same time, we'd really like to get to call it 1.0 or first release I'm not ashamed of, or whatever, of these interfaces, to be able to say, like, all right, well, we've from a community standpoint, we've looked at these interfaces and they look like they have all the pieces that we need. And inside those interfaces is functionality to be able to do device and node management. So the device management is when you have an infrastructure device, it's separated from the host now, and now you need to manage it. So it needs to be part of your fleet. It might crash. It may need new software. It may need to do everything that another host or another switch would need. So that needs to be part of these interfaces that we define. And as maybe a side effect of that, because these infrastructure devices are independent, they can also be used not only to manage themselves, but also to manage the host that they're sitting inside of. So they may, be the mechanism by which you image the host, or maybe you use it to image the VMs that are running inside the host. So there's lots of sort of follow-on functionality there where you can use this control plane that you're establishing inside the infrastructure. You can use that to manage the things that are happening inside of the compute. And I'm going to go to those interfaces next after I finish here. Any questions on that? Cool. And then the last part, we have some folks that have been working on this and hope to put out some of the recipe pretty soon so that people can get a visibility as to what's happening here. Is that we're looking to try to find a good API. It's based on P4 that you could use for some of these inline accelerators. And the inline accelerator sort of sits on top of the first two stages before it. So that inline accelerator could be sitting inside the infrastructure. It could be sitting on a bare metal host. It could be sitting in a VM, sitting inside of a container even. And it wants to have some API, like an RPC, not a functional API, but some sort of interface where it can call into the infrastructure and say, well, I want these things to be, either pre-processed or post-processed on my behalf, so that I can, maybe I'm a firewall or intrusion detection function, and I say, well, you don't need to send me the Zoom traffic. I don't need to see that. So maybe just sample it to me, and you can just send that where it needs to go. That type of functionality would be really useful to have, and helps the application scale up, take advantage of an accelerated infrastructure. And so that's the type of interface we want to go and define. And that interface is at the application level, not at the target level. So it's the infrastructure application interface at the top. And just as sort of a bin list of things that we're tracking but aren't able to immediately get to are things like TLS and reliable transport, which become really important pieces as we build upon the functionality. So we put it in the third bin, may actually be broken out into multiple pieces as they come in. And tomorrow, next week's event, I think other folks are going to be talking about even more use cases than I could fit on this slide. And so as they come up, and we are developing them here or in other open source forums, maybe new features will come in and potentially jump the line depending on how important they are. But we have a solid set of functions that we want to add around the first three recipes that we've already published. So we'll continue to chunk through those over time. And our intention is to have these work for the targets that we've published. So definitely KVM obviously as the software baseline, but also the IPUs that Intel's announced, and also the Tofino switch. So the Tofino switch is interesting. It doesn't have the capability to do things like expose storage devices on a host, but it can still do a lot of these usages where we're programming the pipeline to do things like tunneling or Kubernetes or whatnot. So we want to keep the capability of being able to run these usages on the switch there in place. And I think we'll find as the set of usages expands, especially like inline acceleration API, then it's like, oh, okay, that actually makes a ton of sense to have a switch option in the set of targets.
Dan, Chris has a question.
Oh, yeah, sorry.
Hey, Dan, when you talked about inline acceleration, you said there was a quest for some kind of a programming interface or P4 interface. Do you mean you want a northbound API and conceptual tables to program it, or you need externs in P4 to specify the data plane, or both? What did you mean?
Definitely the former. So yeah, externs in P4 are really hard to work with. Maybe you probably know better than I do. It's just, it's hard to make that standard. Everyone's got like going to write their extern totally different, even if they do the same function. So, the thought was to use P4 runtime specifically to create a way to allow these accelerators to have an interface to offload, and maybe they get their own, or they could have special interfaces that have special properties, these type of things. So that was sort of the idea. It's certainly, there's all sorts of complexity there. You wouldn't want to be sending every single new TCP connection to that type of interface. So it has to be sufficiently abstracted. Potentially, P4 is still too low of an abstraction for that, but that's where we're starting. We're starting with P4 to use it as a known quantity in terms of defining an interface to give these applications themselves a little bit of acceleration.
Yeah, it probably makes sense to get input from other DPU smart NIC vendors, because some people probably solve this their own way too. And if there was a standard way, then we'd all have a standard way of programming it.
Yeah, there are some really interesting projects. I think Dash is definitely in the right direction in terms of, it's similar to the first two that I have here, but there's been a couple other projects that look really interesting. They're running on DPUs we want to be influenced by and take that as prior art,
Right.
in terms of making sure that we're learning from what's already out there in the open source.
Thanks.
Yeah, so that's upcoming, I would say, sort of a longer term, and just like you're saying, that we can get feedback, and that's why we'll put it out there early, even if we don't have tons of implementation, to get feedback from people on the interface. Okay, any other questions? I didn't see it. It didn't tell me that. Okay. So let me switch over to back to the website. And that's my last topic. So then I will get people out of there, and we can continue any discussion on Slack or whatnot. Why can't I find the website? Here it is. Okay. All right. So in the documentations tab, I added these two interfaces. I really should post the original picture so people can see that, or actually I'll go back here, is that, the infrastructure application interface is at the top. It's meant to be a sort of RPC based and used to, meaning you're coming in to the infrastructure device, whether it's the server serving VMs or it's a separate DPU, IPU. To have an RPC, to configure it, to set up the network, set up the storage, whatnot. So sort of coming from the outside. While the target abstraction interface is a functional interface, and it's definitely within that system, within the server, within the device. And so, and if we can sort of use these as the bounding box of what goes in IPDK, then that can help us sort of define what are the bits and pieces that we need to assemble here in the middle. And so I put some description of the application interface. What we've been focused on so far has been around here. It's easier to just look at this picture. Has been around OpenConfig and P4 runtime. With the new storage recipe changes, we'll also talk about a sort of generic storage protocol. So we leave that unspecified as to exactly what that is. But you can imagine you need a protocol that says, all right, well, this instance is wanting their disk to be inserted into this VM. and that disk maps to, you know, sort of this logical, you know, it lives in the storage backend in this location, and so the protocol is just adding this mapping to the infrastructure, so that when those requests come in, they get sent over the network to the right place. And it's really similar to what you're doing over P4 runtime, which is, you know, the cloud management systems coming in saying, I want this port to be added into this VM or into this bare metal system. That port maps to this virtual domain, virtual layer 2, virtual layer 3, and all the tunnels and routes and ACLs that you need for that domain get programmed through P4 runtime. So they're very similar. So you end up with these types of interfaces at the top. The IPDK IPU container, I should need the word IPU in there, or not really, IPU DPU container, is taking all of these pieces and providing an example of how the application interface can be implemented. So it's probably not the only way to implement this interface, but it becomes a reference to have all these different pieces in here, and want to be able to specify this in a way that, you know, sort of many things are optional, so that, you know, if you don't have Envoy, you don't have Kubernetes, it doesn't matter, you know, you can still have this infrastructure interface. So need some way to be able to sort of negotiate that, or at least detect, you know, what are the pieces of the application interfaces that are hot and they're alive. We also put in here the idea or the concept of having some sort of redfish, some sort of management interface to be able to handle the case where that infrastructure device is separate from the host and needs its own management. So we put that there, but the further detail as to what types of things you would be able to configure over redfish are in the target abstraction interface. So, you know, going back to that one, the target abstraction interface at the bottom is trying to find commonality across these, you know, different types of devices. And they also, you know, follow really tightly what was defined in the application interface. So, like in the application interface, you have virtual devices that get set up through OpenConfig, and so now you need an interface to your target to be able to take those OpenConfig schemas, say whatever, add a disk, or, you know, set the port speed of an interface. You have to have the target function that goes and does that. And so that's where, you know, the target abstraction interface kind of maps from that. And as opposed to the previous interface, which is RPC based, this is going to be sort of library based. The API, the functional interface, also drivers to move data around, really similar to, you know, any sort of switch or you know, sort of smart NIC interface that you would have seen in the past. Try to make it sort of unsurprising, like, oh, okay, I know what that looks like. So we talked through the types of virtual devices that we're targeting right now. You know, the virtual devices, we're trying to pick versions of or device implementations that are open, or they have a standard, lots of people behind them, and they also have a software equivalent so that, you know, they have to run in the KVM target. We have a bunch of different functions for managing the life cycle of these different devices, like power up and down, reboot, recovery, things like that. And then the last piece is the control of the accelerators. So if you think of the pipeline that you might have on these DPU, IPU things, and also, you know, how do I manage the link? You know, if it has its own Ethernet link, how do I manage that? and we have essentially borrowed the functionality that you use to manage a switch link, even if in many cases that link is a NIC interface. So we try to find that there's a lot of commonality there, and because we're using OpenConfig, we're kind of coming with the background of a programmable switch, or even just a just a layer 2, layer 3 switch. And that's also where we sort of have a tie-in with SCI. Something that we would like to do in the near future is to be able to have Sonic be an option inside IPDK, sort of maybe a medium or longer term thing that we'd like to have. But we've been trying to keep in sync with the things that are happening inside of Sonic, where Sonic has had P4 added and things like that, trying to keep that in sync with what we're doing here. Yeah, and there was mention earlier today about the NetDev and sort of the exception handling. This is even going back to the Sonic Pins project. That was sort of a big deal to go and specify. So I hope to see that specification of that here. It's like, okay, well, how do I trap traffic back to the infrastructure? Can I have control over how that data is presented? Can I have it go to the kernel or user space? All of that type of control, just like you would have in a switch, you would want to have here. So these are on the website now. We'll continue to add them over time, and like we said, our target is to get these to a 1.0 in subsequent releases. This is just a starting point. Okay, any questions on that? Cool. All right, that was all I had. I'm going to switch back to that slide deck. And any questions that we want to put on the recording? If not, we'll stop it. PowerPoint live. No, that's not what I wanted to do. Oh, interesting. Okay. No, I don't want to do that. Any other questions? Cool. So let's stop the recording. Do that. Maybe. Okay, cool.